Okay, thank you. So thank you for inviting me. It's an honor to talk here. So I'm Omer Barkol. I'm a research manager in HP Labs. And I'll talk about the machine and how it changes software stack. And the machine is the name of a project, and we'll get to that. And just to say, you don't have to read it. I just want to show you. This is just to say that this is a research. It's not a promise for any product. And we do hope to make it a very big product and actually to transfer a lot of technology out of this project, but for now it's a research project. So just a little bit about where I come from. So unlike Bianca, who crossed the world just to talk here, I crossed the Technion. I came from HP Labs here in the Technion. We are part of the HP Labs, which resides mainly the headquarters are in Palo Alto. We have a big branch in Bristol, England, and here in Haifa is the third site. We have 5 research labs inside the lab, and we are a big chunk of the analytics lab. So this is just. And we just, last year, we celebrated the 20th year. It was, the site here in Haifa was initiated by Professor Abram Lempo. So this is kind of a motivation slide, right? I don't know if I need to motivate you about why we need to handle big data, but we have different reasons to think we don't have the answer for what we need today. And either it's because of what we have, so like the magnitude of the data and the flush of a legacy database, whether it's requirements that are changing and increasing the way the people want to consume the data, what insight they want to get from the data, and perhaps most the restriction we have on the hardware. So for example, how much electricity we can afford to use in order to extract information from data. I think this is a very important case because many companies, many enterprises, which are our customers, they have a lot of data. They really have, and we all know that you can extract gold from data. But actually, the gold is very, very scarce in the big data, right? And the amount of investment that you have to put in order to extract the knowledge that will then translate into money for the company has to be worthwhile, right? So you can't, even if theoretically you can do a great big data analytics on it, you won't invest it because it won't give you the return on your investment. And the last past years, computer architecture have the same kind of ideas of having the compute. Next to it, you have the memory. More far away, you have your storage. And this is the way it has been going on. Of course, it's been improved all the time. In HP Labs, and I'm jumping a little bit about what do we do there. So we do research for HP. We work with our business units in order to create, to look a little bit farther ahead into the future, look what's coming, help them create new technology, and of course, being part of the community, advancing the state of the art. A lot of the time, it's really can be the part of what is going on inside the business unit. Sometimes it's something that creates totally new areas for HP. So, you know, the inkjet, for example, inkjet printer, which became a very large business, of course. We also, at HP Labs, were part of the commercialized RISC chips in the 80s. And so I highlight things that are really part of changing the architecture of computers. And Last year, the HP Moonshot, which are cartridges of very low energy socks for servers. So what is the machine? The machine is a very exciting and ambitious research project in HP Labs. It is actually handled by a lot of the people in HP Labs. So throughout the labs of HP Labs, both mainly the system lab, but of course the cloud and security lab, the analytics lab, the networking lab, we're all involved in this interesting project. It was announced a year ago in what is called HP Discover. By the way, tomorrow starts another HP Discover. And if this talk interests you, you're welcome to go into the site, search for HP Discover, and in the following days there will be all kind of additional announcements for different parts of HP's activity, but also on this part. So if there is one thing I want you to remember from this talk, like symbolically, it's this very simple thing. So the idea is that the machine doesn't take the compute and put the memory next to it and then far away put the storage. It actually have the compute in one place, and then through photonics connection, connects to memory that is persistent. And once the memory is persistent, you actually don't really need storage. So we'll get to it. So special purpose cores, of course, this is an industry trend. And we, as I said, we have also been part of this trend in our HP Moonshot product. In photonics, we have a very big research around how do you put photonics really into the system so that it goes all the way to connecting your CPU to your memory, etc., and not only to farther away places. Sorry. And as for the memory pool, so this is also part of a thing that is happening, which is non-volatile memory. So HP itself has its own research around non-volatile memory, or which in particular can be used to be non-volatile RAM, random access memory. So just to say like 2 words, so who heard about Memristor? Okay, like about a third of the crowd. So I just say like in 2 sentences what it is. It's kind of interesting. So you know resistors, you know capacitors, so you have different components of electricity. So Memristor is actually one that was only theoretically assumed, but was found actually in HP Labs in 2007. And if you want to think what it is, so think you have a resistor, right? It has the resistance, and if you flow current through it, it will save its resistance, right? Perhaps if you heat it a lot, it will change its resistance, but later on, if it cools down, it will have the same resistance it had when it got out of the factory. Now, a memristor is different in a way that if you flow current through it above certain threshold, it will change its resistance. And it will change it until you flow it again on the other direction. So it is a way to think about a resistor that you can write into it, and then it remembers what you wanted to write there. And that's the whole, that's the way. So if you can produce it and put it on a material, you can actually have a random access array that doesn't have to have, unlike DRAM, it doesn't have to have power in order to persist or to remember what it's written into. Okay, so And I'll just want to add one more thing, that the architecture change is not dependent on the NVRAM technology. So there are other, as I said, other technologies that are worked on. And of course, the same architecture change could happen with other NVRAM technologies. So what does it give if you have such a way to do non-volatile memory and non-volatile RAM? So this is kind of the speed that takes you to go to either one of the hierarchies part of the computer. So if a processing cycle would consider as 1 second, then the SRAM, the caches would take 5 seconds. The DRAM is already 2 minutes. And then once you want to go to a persistent store, it will take you days, months, and years. So this is a heavy payment to pay in order to persist things that you want to persist. So this is the way it looks like, the different layers of the memory, and here in purple is the ones that are persistent, so the ones that you have to write to if you want your results to persist. So you have the main memory, and then if you want to persist, you have to go to SSD or disk. Now, if you have NVRAM, you can collapse this hierarchy, right? So assuming your NVRAM is as fast as your DRAM, you don't need any of, and you can produce many of it. You don't need all of these. You just can collapse all those together and have them together. Now this is very weird, right? Because we have storage and we have memory and we use them for totally different tasks. But one has to ask himself whether we use them in different ways because this is the way we want to, or this is the way we have to, right? Whether we serialize things into the disk because we like serial things, or because the disk is serial, right? So, and about the size of it. So, as I said, you can think of a cartridge where you have this compute and this non-volatile memory connected with photonics, and you can think of an enclosure of such a thing. You can think of a rack full of this thing, and you can think of 160 racks full of this thing. So this is because of the photonics and the way it is connected, this is scalable in a very, very efficient way. Of course, it presents a lot of challenges, and I'll talk about them in a minute. It doesn't come for free. So, as you understood, I'm not a hardware person, and I can say it now. I'm telling you about a very big project that involves hundreds of people, right? So whenever you ask me a question that either I don't know the answer, or I can't tell you the answer, and I can mix between the two. So, but I hope to answer your question anyway. So we didn't get to questions yet. I want to talk now about the software stack that is the result of these changes in the hardware. So we have this new concept of this new hardware and new architecture of the hardware. And we want to ask ourselves, okay, so now how does the software stack look like once we change this architecture? What does the machine's operating system look like? Is it like a one operating system for this big thing? Is it single, like just a cluster? Is it a different thing? Remember, we have now storage, which is it's based on random access memory and not serial. We have the management of such a big nodes. We have algorithms and we have analytics. And of course, we have the security for the entire stack from hardware to the analytics all the way up. And the main question is that we ask ourselves is how do we help our customer create better value and cheaper value from their data using this new capabilities. So there are different aspects and they're kind of orthogonal, so I didn't mean to, it kind of looks like the performance and simplicity graph, and these are not necessarily like, I thought of them as orthogonal to each other. So we have different aspects of how we think about the advantages that can come out of such changes. So one is perhaps you can get better performance out of these changes. And I'll give you a few examples of our thoughts of where can it help us in special workloads that we think that are most, might most enjoy from such a change. Second thing is about simplicity, and it could be that in some cases it will add complexity, but we hope that in a sense it will add simplicity, and I'll give you examples of our thoughts about this. And of course there's new opportunities and challenges once you present a new paradigm all together. So remember the challenge, the opportunities here that we have very large non-volatile memory that we can use both for memory and storage. Once it's in this case, you have a photonics, it's very fast and you can load store. So actually, if you think about it as a cluster, you can still go from one node and go to the memory, directly to the memory of the other node and load from there. So it's actually kind of confusing, yeah, right? And I'll talk about this in a minute. There are many hardware threads per sock. This is quite standard. A lot of fast local DRAM. So when we talk about DRAM and NVRAM and whether they coexist or not, this is really dependent on the times and whether the non-volatile memory we'll get will be as fast as the DRAM or not, and this might change throughout the years. Here, I also want to talk about cache coherence. So when you think about, I don't know, a mainframe or a high-performance computer, you think about shared memory, big shared memory with everything is like coherent and and when you think about a cluster, you think about each one is a node, they talk to each other through communication, and nothing is shared, right? And the thing is that when we think about the machine, we often think of where if shared nothing is the cluster case and shared everything is the, let's say, mainframe or, in a sense, high-performance computing, this new paradigm is mostly a share something case, okay? You have accessibility, so you have this network, this fabric where you can go from your local compute to any place, load from there, and of course this might be a problem in synchronization, and how do you leverage this without doing stuff that is wrong? But it is the capabilities that might be usable in certain cases. So if we look at I'm talking about the operating system and how it's influenced. If we look on as I said, we concentrate here for now on the memory and storage. We add the NVRAM, and now we ask ourselves, okay, in the storage part, this is also now addresses in which are random accessed, and now we think of the entire memory as global virtual addresses, so we can approach any address in our entire address space, both in memory and in storage. So if everything is random access is not in files, then there are a lot of changes that we have to consider. As I said, the synchronization is different, but also we don't need the page caches and what reside. Security, I don't want to talk too much. Of course, there are a lot of issues around security. I just want you to think about the fact that since the memory is persistent, it is easier to recover, so we have advantages in the recovery. On the other hand, if we go down and we go up, everything is still in memory, right? So sometimes we use the fact that memory erases as a kind of a nice feature, right? People like their program to crash because then they know they start from scratch. About simplicity, so this is a kind of a example of how you would write a website, and now you have a query. Bring me the n, posts with the comments. So you have to take the tag, you have to put it into your SQL query. You have to see whether it's already cached, because you know that you don't want to query things that you already cached. If you want to cache it, if you already cached it, you have to deserialize it from the cache. If you didn't, you go to the database, you bring it, then you cache it for next time. Then you start to read what you have. And actually, once you have the post, if they have comments, you go again to the database. So this is another function that actually inside of it has another SQL query for the comments of this post. And you add this to this data structure that you create here, right? That you eventually will return, which is just a linked list of posts with the comments, right? This is what you wanted, a linked list of posts and their comments, right? And this is the way code looks like when you work with I/O and you have to go to the disk, etc. What you would like it to look like is like a second-year student's code, which is just, I have this data structure, I go to my data structure, you write libraries, books, etc., and just give me the posts and comments and the nth part, and that's all. That's the simple code we would like to have. And this is what we have because of the mechanism of serialization and the fact that we hold everything in databases, etc. So what if we didn't have to put everything in files, in XMLs, in databases, etc.? What if we could persist our stuff just as data structures in a persistent way, right? And the fact that it could be that this will reduce a lot the cognitive load of programmers. Actually, we did a small survey of corpus of programs, and we looked at how many things are not the actual logic of the program, but other things that are dealt with. So the most 5 frequent things were storage, user interface, exception handling, multi-threading, and string processing. And these are things that are adding cognitive load on the programmers when they deal with them. The red ones are the ones that are related to the going to your XML file, bringing in it, handling the exception and the problem with failing on going to the disk, right? This is what makes you a lot of time fail. And a lot of time, this string processing also related to XMLs and stuff that comes from disk. So a lot of the cognitive and a lot of the overhead of programs as they are written today is because of I/O. That is not because of I/O of going to the user interface, because user interface we'll always have to have, right? If we have users. But other than that, we could reduce a lot of the complexity in our systems. I want to say a few words on analytics. So I did the same. Of course, we want to support the state of the art. That's also so everything that runs today, we want it to run also on the machine with performance at least as good, right? We also want to have things that have better performance, and I'll talk about those in a minute. Another thing is to democratize advanced analytics. So there's a lot of things that Google can do because they have this huge cluster and they have a lot of money. But if Avis want to do that, they can't create a cluster like Google's, right? They're Avis. That's not their core business. So they won't create a huge cluster to do advanced analytics. But it could be, and we have reason to believe that we could, with that means, democratize some of the machine learning and analytics tasks. And we hope there is new opportunities altogether with this architecture. So here, a few examples. First one is graph analytics. So graph analytics is quite hard. Graph analytics, so it depends what kind of analytics, but almost every graph analytics which is not embarrassingly parallel is hard because you have to jump all the time and your nodes, well, I'll say vertices because nodes are something else in this. So your vertices and edges are scattered all around and you have to all the time go, and so the random access kills you because you pay the latency to the disk all the time. And here, if your representation, and I'm talking about huge graphs, if your representation here is the persistent representation is in random access persistence, then your capabilities might really dramatically change. A second area is search state optimization. So today, when you think about like, take for example, computers playing poker. Okay, I talked with this guy, and their research is to create poker games. They use today a cluster of like 200 nodes, which is almost 5,000 cores, and the RAM that they have is about 15 terabytes. Okay, this is the cluster they have. So, and they all the time use the compression and stuff because the memory is so they can't use the disk. Disk is totally out of question. So I asked him, what happens if you have 10 times, 100 times more memory? And this changes everything, right? This changes the way you think about these kind of tasks. Deep learning is the same, and I just want to say one thing about distributed mesh computing. So this is a different angle on how you can use nonvolatile memory. Instead of going to the big machines, you can use it actually on kind of Internet of Things. So keep the data where it's created, and then if 99% or 99.999% of the data is unusable, you don't pay for bringing it to a big server to analyze it because it won't pay on even the communication of sending it, it won't pay for it. But if something you want to analyze it in a certain way together, you might be able to do that. And in order to support that, you have a lot of the IoT cases, you don't have a way to put a disk, etc., in the nodes. You have to put something that is low power, etc. And that's also kind of an application for this technology. So just a quote of Perlis: adapting old programs to fit new machines usually means adapting new machines to behave like old ones. So I think that once you're given a new machine, it's better to think about it real carefully and think how your application or your area might be changing. So I want to thank you. This is my contact. We do want to approach the community. We do want to, we will have a simulator and stuff. So if you want and you're interested in some aspects of this, please approach. And thank you for listening.